Sometimes people talk about support vector machines as large margin classifiers. In this video, I'd like to tell you what that means, and this will also give us a useful picture of what an SVM hypothesis may look like. Here's my cost function for the support vector machine, where here on the left, I've plotted my cost1 of z function that I use for the positive examples, and on the right, I've plotted my cost0 of z function, where I have here z on the horizontal axis. Now, let's think about what it takes to make these cost functions small. If you have a positive example, so if y is equal to 1, then cost1 of z is 0 only when z is greater than or equal to 1. So in other words, if you have a positive example, we really want theta transpose x to be greater than or equal to 1. And conversely, if y is equal to 0, look at this cos0 of z function, then is only in this region, where z is less than or equal to 1, that we have that cos0 of z is equal to 0. And this is an interesting property of the support vector machine, right? Which is that if you have a positive example, so if y is equal to 1, then all we really need is that theta transpose x is greater than or equal to 0, and that will mean that we classify correctly. Because if theta transpose x is greater than 0, our hypothesis will predict 0. And similarly, if you have a negative example, then really all we want is that theta transpose x is less than 0, and that will make sure we got the example right. But the support vector machine wants a bit more than that. It says, don't just barely get the example right? So then don't just have it just a little bit bigger than 0. What I really want is for this to be quite a lot bigger than 0, say maybe greater than or equal to 1, and I want this to be much less than 0, maybe I want it less than or equal to -1. And so this builds in an extra safety factor or safety margin factor into the support vector machine. Logistic regression does something similar too, of course, but let's see what happens, or let's see what the consequences of this are in the context of a support vector machine. Concretely, what I'd like to do next is consider a case where we set this constant c to be a very large value. So let's imagine we set c to a very large value, maybe 100,000, some huge number. Let's see what a support vector machine will do. If c is very, very large, then when minimizing this optimization objective, we're going to be highly motivated to choose a value so that this first term is equal to 0. So let's try to understand the optimization problem in the context of what would it take to make this first term in the objective equal to 0, because maybe we'll set c to some huge constant. And this should give us additional intuition about what sort of hypotheses a support vector machine learns. So we saw already that whenever you have a training example with a label of y equals 1, if you want to make that first term 0, what you need is to find the value of theta so that theta transpose xi is greater than or equal to 1. And similarly, whenever we have an example with label 0, in order to make sure that the cos0 of z, in order to make sure that cost is 0, we need that theta transpose xi is less than or equal to -1. So if we think of our optimization problem as now really choosing parameters to ensure that this first term is equal to 0, what we're left with is the following optimization problem. We're going to minimize that first term 0, so c times 0, because we're going to choose parameters so that it's equal to 0, plus 1/2, and then that second term. And this first term, that's c times 0, so let's just cross that out because I know that's going to be 0. And this will be subject to the constraint that theta transpose xi is greater than or equal to 1 if yi is equal to 1, and theta transpose xi is less than or equal to -1 whenever you have a negative example. And it turns out that when you solve this optimization problem, when you minimize this as a function of the parameters theta, you get a very interesting decision boundary. Concretely, if you look at a data set like this with positive and negative examples, this data is linearly separable. And by that, I mean that there exists a straight line, or there exists many different straight lines that can separate the positive and negative examples perfectly. For example, here's one decision boundary that separates the positive and negative examples. But somehow that doesn't look like a very natural one, right? Or if I draw an even worse one, here's another decision boundary that separates the positive and negative examples, but just barely. But neither of those seem like particularly good choices. The support vector machine will instead choose this decision boundary, which I'm drawing in black. And that seems like a much better decision boundary than either of the ones that I drew in magenta or in green. The black line seems like a more robust separator that, just does a better job separating the positive and negative examples. And mathematically, what that does is this black decision boundary, it has a larger distance. And that distance is called the margin. But if I draw these two extra blue lines, we see that the black decision boundary, it has some, larger minimum distance from any of my training examples, whereas the magenta and the green lines, they come awfully close to the training examples, and that seems to do a less good job separating the positive and negative clauses than my black line. And so this distance is called the margin of the support vector machine, and this gives the SVM a certain robustness because it tries to separate the data with as large a margin as possible. So the support vector machine is sometimes also called a large margin classifier, and this is actually a consequence of the optimization problem we wrote down on the previous slide. I know that you might be wondering, how is it that the optimization problem I wrote down on the previous slide, how does that lead to this large margin classifier? I know I haven't explained that yet, and in the next video I'm going to sketch a little bit of the intuition about why that optimization problem gives us this large margin classifier. But this is a useful picture to keep in mind if you're trying to understand what are the sorts of hypotheses that an SVM will choose, that is trying to separate the positive and negative examples with as big a margin as possible. I want to say one last thing about large margin classifiers and this intuition. So we worked out this large margin classification setting in the case of when C, that regularization constant, was very large, right? I think I said that to 100,000 or something. So given a data set like this, maybe we'll choose that decision boundary that separates the positive and negative examples with a large margin. Now, the SVM is actually slightly more sophisticated than this large margin view might suggest. And in particular, if all you're doing is use a large margin classifier, then your learning algorithms can be sensitive to outliers. So let's say I add an extra positive example like that shown on the screen. If you add one example, then it seems as if to separate the data with a large margin, maybe I'll end up learning a decision boundary like that, right? That is the magenta line. And it's really not clear that based on a single outlier, based on like a single example, it's really not clear that it's such a good idea to change my decision boundary from the black one over to the magenta one. So if the regularization parameter C were very large, then this is actually what the SVM will do. It'll change the decision boundary from the black to the magenta one. But if C were reasonably small, or if you were to use C not too large, then you still end up with this black decision boundary. And of course, if the data were not linearly separable, so if you had some positive examples in here, or if you had some negative examples in here, then the SVM will also do the right thing. And so this picture of a large margin classifier, that's really the picture that gives better intuition only for the case of when the regularization parameter C is very large. And just to remind you, this corresponds, C plays a role similar to 1 over lambda, where lambda is the regularization parameter we had previously, and so it's only if 1 over lambda is very large, or equivalently if lambda is very small, that you end up with things like this magenta decision boundary. But in practice, when applying support vector machines, when C is not very, very large like that, it can do a better job ignoring a few outliers like here, and it'll also do reasonable things even if your data is not linearly separable. But when we talk about bias and variance in the context of support vector machines, which we'll do a little bit later, hopefully all of these trade-offs involving the regularization parameter will become clearer at that time. So I hope that gives some intuition about how the support vector machine functions as a large margin classifier that tries to separate the data with a large margin. Technically, this picture or this view is true only when the parameter C is very large, but it's a useful way to think about support vector machines. There was one missing step in this video, which is why is it that optimization problem we wrote down on these slides, how does that actually lead to the large margin classifier? I didn't do that in this video. In the next video, I will sketch a little bit more of the math behind that to explain that step in the reasoning of how the optimization problem we wrote out results in a large margin classifier.